There are places in our universe where the laws of physics completely break down, where time itself can stop and space gets torn to pieces. These are black holes, and what we've discovered inside them defies imagination. For decades, black holes were purely theoretical constructs. Today, we have direct evidence they're real, and they're everywhere. But first, we must address a critical misconception. Black holes are not empty voids, they're the opposite. They represent matter compressed to densities that challenge comprehension. Consider a star with 10 times the mass of our Sun. When it collapses, its entire mass compresses to a mathematical point. The resulting gravity becomes so extreme that escape becomes physically impossible. Even electromagnetic radiation cannot overcome this gravitational pull. This renders black holes effectively invisible, which makes them profoundly mysterious. Einstein's general relativity revolutionized our understanding. Black holes don't simply attract matter, they fundamentally warp spacetime. Imagine spacetime as a flexible membrane under tension. A black hole creates an extreme depression in this four-dimensional continuum. This warping defines what we call the event horizon. The event horizon represents a boundary from which return becomes impossible. Beyond this threshold, all paths lead inexorably toward the singularity. What transpires during a hypothetical descent into a black hole? Professor Brenna Mockler of UC Davis provides fascinating insights. Upon crossing the event horizon, one's temporal dimension orients inward. Light propagates exclusively toward the center at this point. All matter follows this unidirectional trajectory without exception. The phenomenon of gravitational time dilation presents a striking paradox. External observers perceive the falling object slowing asymptotically. From their vantage point, it appears frozen at the horizon indefinitely. Yet for the falling observer, the passage seems entirely ordinary. The horizon crossing occurs without locally observable discontinuity. However, survival assumes one escapes a catastrophic process. This bears the technical designation of spaghettification. Despite its informal nomenclature, this appears in astrophysical literature. The gravitational gradient across extended objects becomes extreme. Differential forces elongate matter along the radial direction. This results in structural disintegration at the molecular level. At the core of every black hole lies an even greater enigma. This is where our theoretical frameworks encounter fundamental limitations. The singularity represents a breakdown of classical spacetime geometry. In non-rotating Schwarzschild black holes, this manifests as a point. Mathematically, infinite density concentrates in zero spatial volume. Such infinities indicate where current physics becomes inadequate. Rotating Kerr black holes exhibit different configurations. Their singularities extend into ring structures rather than points. These systems also possess an inner Cauchy horizon. This region exhibits severe spacetime instabilities. Approaching this boundary exposes one to accumulated radiation. Energy density approaches theoretical maximums in this zone. All infalling matter and radiation converge at this location. The interaction timescale approaches zero. Temperature measurements defy conventional description. Temperatures so extreme they approach the theoretical limits of physics itself. Understanding the matter density requires extraordinary perspective. Consider aggregating all observable matter throughout the cosmos. Every stellar system in every galaxy across visible space. Compress this to dimensions smaller than atomic scales. This approximates Planck density, the condition within black holes. Only the Big Bang singularity rivals such extremes. We must acknowledge the speculative nature of these descriptions. Direct observational confirmation of interiors remains physically impossible. Our understanding derives entirely from mathematical extrapolation. Beyond the event horizon, general relativity may require modification. Alternative theoretical frameworks suggest singularities might not form. Quantum gravitational effects could prevent infinite compression. Some models propose exotic matter configurations instead. Graver stars, for instance, replace singularities with dark energy. Wormhole solutions emerge naturally from Einstein's field equations. However, such structures prove intrinsically unstable. Observational astronomy focuses on effects rather than interiors. These effects manifest dramatically in surrounding matter dynamics. Black holes actively accrete material from their environments, gas, interstellar dust, and occasionally stars fall under their influence. This material organizes into rotating accretion disks. Angular momentum conservation creates these spiraling structures. Friction within disks generates tremendous thermal energy. Temperatures reach millions of degrees Kelvin. At such extremes, matter emits intense X-ray radiation. This radiation provides our primary detection methodology. While black holes remain invisible, their accretion signatures are unmistakable. Supermassive black holes exhibit additional remarkable phenomena. Relativistic jets emerge perpendicular to accretion disks. These jets transport matter at velocities approaching light speed. Their influence extends across galactic scales. Jet energy input regulates star formation in host galaxies. Current research indicates coevolution between black holes and galaxies. Their growth histories appear intimately connected. Empirical correlations link black hole mass to galactic properties. This relationship persists across cosmic time. Observational surveys confirm supermassive black holes in most large galaxies. Our Milky Way contains such an object, Sagittarius A star. Its mass approximates 4 million solar masses. Currently, this object exhibits relatively low activity levels. Future galactic dynamics may alter this equilibrium. The Andromeda galaxy approaches through intergalactic space. Previous models predicted inevitable collision within 5 billion years. Recent research published in 2025 revises this dramatically. Current probability estimates suggest only 50% merger likelihood. Should collision occur, central black holes would eventually coalesce. This process generates powerful gravitational radiation. Such waves propagate throughout spacetime. Gravitational wave astronomy has detected similar events. Facilities like LIGO and Virgo monitor for these signatures. Regarding longevity, Stephen Hawking proposed remarkable predictions. Through quantum processes, black holes emit thermal radiation. This Hawking radiation causes gradual mass loss. For supermassive black holes, evaporation timescales are extraordinary. A Google years represents the approximate duration. This vastly exceeds current cosmic age. Eventually, complete evaporation would occur. The final emission marks a black hole's termination. Universal black hole evaporation signifies a cosmic transition. This represents one theoretical end state for our universe. In conclusion, black hole interiors remain largely mysterious. Our knowledge rests on theoretical foundations awaiting validation. Yet they represent crucial laboratories for fundamental physics. They test theories under the most extreme conditions nature provides. Contemporary research employs advanced computational methods. Quantum computing and artificial intelligence assist theoretical modeling. Future observations may provide unprecedented insights. Until then, black holes remain among science's greatest challenges. These cosmic objects remind us of profound universal mysteries. They represent frontiers where understanding meets its current limits. And in confronting the unknown, science continues its eternal quest for truth.